right now. Not someday, right now. While you're reading this, every charge cycle is quietly murdering it. 1 degree of heat and 1 microscopic crack at a time. And for 30 years, the entire tech industry has just asked you to accept that. Buy a new phone, buy a new laptop, buy a new battery pack, repeat forever. Japan just said no. And by the end of this video, you're going to understand something that almost nobody talks about. The battery sitting in your phone was never actually finished. It was rushed. It was a compromise, dressed up as a miracle. And a quiet, decades-long campaign by Japanese scientists and engineers has been working to replace it from 4 completely different directions at once. One of those directions doesn't even involve a battery anymore. It involves electricity flying through the air like a radio signal, landing directly on your device with nothing in between. Stay with me, because the last part of this story involves a satellite in orbit, a beam of microwaves, and a demonstration that sounds like it was ripped out of a comic book. Except it actually happened. Let's start with the man almost nobody has heard of, because his story is the reason you're even holding a smartphone right now. His name is Akira Yoshino. In the early 1980s, working for a chemical company in Japan, Yoshino was trying to solve a problem nobody had cracked. How do you build a battery that's actually rechargeable, lightweight, and powerful enough to matter? Every battery before his used chemistries that were heavy, unstable, or wore out fast. Yoshino built the first practical lithium-ion battery using a carbon-based anode instead of the raw lithium metal that kept causing fires in earlier experimental designs. Sony commercialized it in 1991. 3 decades later, in 2019, Yoshino won the Nobel Prize in Chemistry for it. Here's the part that should stop you cold. Nearly every phone, laptop, and electric car on Earth today is still running on a chemistry that is, at its core, the same one Yoshino invented over 40 years ago. We've made it smaller. We've made it denser. We have not fixed its actual problems. We've just gotten better at hiding them. So what's actually wrong with it? 3 things. And once you see them, you can't unsee them. First, dendrites. Every time you charge a lithium-ion battery, lithium ions move from one side to the other and ideally settle down neatly. But they don't always settle neatly. Sometimes they build up in tiny, jagged, metallic spikes called dendrites, growing inside the battery like frost on a window. Eventually, a dendrite can pierce the thin separator inside the cell and cause a short circuit. That's not a hypothetical. That's exactly what caused Samsung to recall and permanently discontinue the Galaxy Note 7 in 2016, after phones started catching fire in people's pockets and on airplanes. Over 1 million units. Gone. Because of microscopic metal spikes nobody could see forming. Second, the liquid. Inside almost every lithium-ion battery is a flammable liquid electrolyte. It's the medium that lets ions move back and forth. It's also, quite literally, fuel. Combine a dendrite puncturing a separator with a flammable liquid electrolyte and you get thermal runaway, a chain reaction where heat builds faster than it can escape until the battery vents, smokes, or ignites. It's rare per device, but multiply that risk across billions of phones, laptops, scooters, and EVs, and rare becomes warehouse fires, cargo plane bans, and a very real design ceiling on how much energy we're willing to pack into a small space. Third, the mining. Cobalt, a key ingredient in most lithium-ion cathodes, comes disproportionately from the Democratic Republic of Congo, where a significant share of production has been linked to artisanal mines with documented child labor and unsafe conditions. This isn't a side issue. It's baked into the supply chain of nearly every battery-powered device made in the last 20 years. So that's the inheritance. A chemistry from the 1980s, prone to internal metal spikes, built around flammable liquid, and dependent on a mining supply chain with a human rights problem attached. And for decades, the industry's answer was simply, make it smaller, make it cheaper, and hope nobody asks too many questions. Japan asked the questions. And just like the story of the microwave being quietly dismantled by multiple companies from multiple angles, the exact same thing has been happening to the battery. Except almost nobody has connected the dots until now. Let's start with the biggest one, Toyota. For years, Toyota has been developing what's widely considered the holy grail of battery technology, the solid-state battery. Instead of a flammable liquid electrolyte, a solid-state battery uses a solid material to move ions between electrodes. No liquid to leak, no liquid to ignite. And because solid electrolytes can physically block dendrite growth far more effectively than liquid ones, the fire risk that's haunted lithium-ion since Yoshino's first prototype drops dramatically. Toyota has partnered with Idemitsu Kosan, a Japanese energy company, to mass-produce a sulfide-based solid electrolyte, one of the trickiest materials in this entire field to manufacture at scale. Toyota has publicly targeted production of solid-state EV batteries around 2027 to 2028, with claims that center on two numbers that sound almost fake: charging to a meaningful range in about 10 minutes, and a driving range approaching 750 miles on a single charge. For comparison, most EVs on the road today take 30 minutes or more for a fast charge and top out closer to 300 miles. If those targets hold, that's not an improvement. That's a different category of product. Quick pause, because this is the point in the story where it's worth asking yourself something. How many pieces of your life are you currently limited by battery anxiety, range anxiety in a car, your phone dying before dinner, your laptop shutting off mid-flight? If that resonates, stick around, because it gets stranger from here. And if you want more breakdowns like this one, subscribe now, because the next section is the part almost no other channel is covering. Second front, Panasonic. Yes, the same company quietly dismantling the microwave. They're doing it to batteries too. Panasonic, alongside Japanese materials companies, has been pushing silicon-based anodes instead of the graphite anodes that have dominated lithium-ion batteries for 30 years. Silicon can theoretically hold roughly 10 times more lithium ions than graphite by weight. The problem historically has been that silicon swells and cracks as it absorbs lithium, destroying the battery after a handful of cycles. Panasonic's approach blends silicon into the anode structure in carefully engineered ratios to capture some of that extra capacity without the material falling apart. Combined with a larger 4680 cell format, a cylindrical cell roughly the size of a soda can, versus the tiny AA battery-size cells used in earlier EVs, Panasonic has been targeting meaningful jumps in energy density for the batteries going into electric vehicles, aiming to squeeze more range out of the same physical space. It's not as flashy as 10-minute charging, but it's the unglamorous, grinding kind of engineering that quietly makes everything else possible. Third front, and this is where the story stops being about a better battery and starts being about no battery at all. In Kyoto, researchers have spent years refining wireless power transfer using magnetic resonance, a way of sending electricity through open air over short distances, not through a wire, but through a synchronized magnetic field between a transmitter and a receiver tuned to the exact same frequency, almost like two tuning forks vibrating in sympathy across a room. It's already quietly showing up in things like electric toothbrush chargers and some phone charging pads. But Japanese researchers have been pushing the range and efficiency of this technology far beyond a countertop pad, working toward powering moving objects, electric buses charging while driving over embedded coils in the road, sensors that never need a battery swap because they simply harvest power from the air around them. And then there's the part of this story that sounds the most like fiction, except it isn't. Japan's space agency, JAXA, working alongside Japanese universities and private companies, has spent years developing and testing technology to beam solar power collected in orbit down to Earth using microwaves, the same category of energy, ironically, that powers the magnetron sitting in your kitchen microwave. The idea is almost absurdly ambitious. Put massive solar collectors in space, where sunlight is constant and unfiltered by atmosphere or weather, convert that energy into a microwave beam, and transmit it precisely to a receiving station on the ground, which converts it back into usable electricity. Japan has run ground-based demonstrations of this concept for years and has stated long-term ambitions to demonstrate this at commercial scale in the coming decades. Zoom out for a second and look at what that actually means. If you can transmit meaningful power wirelessly, through the air, over distance, continuously, the entire premise of store energy in a box you carry around starts to look temporary. A battery is a workaround for a world where power isn't available where you need it, when you need it. Wireless power transfer is Japan's long bet that the workaround itself might eventually become unnecessary. And there's a fourth front, quieter than the rest, that attacks a completely different weakness: sodium. Lithium is genuinely rare in accessible, high-grade deposits, expensive to mine, and geopolitically concentrated in a small number of countries. Sodium, on the other hand, is one of the most abundant elements on the planet. It's sitting in seawater everywhere. Japanese research institutions have been working on sodium-ion battery chemistries as a cheaper, more geographically flexible alternative to lithium, especially for stationary energy storage. The giant battery banks that store solar and wind power for the grid, where extreme energy density matters less than cost and abundance. Sodium-ion batteries won't replace the battery in your phone anytime soon. Energy density isn't there yet, but they attack the supply chain problem lithium can never fully escape. So look at what's actually on the table, all at once. Toyota, attacking the fire risk and charging speed with solid electrolytes. Panasonic attacking energy density with silicon anodes. Kyoto's wireless power research and JAXA's space-based transmission attacking the idea that you need stored energy at all. And sodium-ion research attacking the ethical and geological weak point buried in every lithium supply chain on Earth. 4 different companies, 4 different institutions, 4 completely different angles, all chipping away at the same 40-year-old compromise Akira Yoshino built in a lab because it was the best anyone could do with 1980s materials science. Here's the part that should genuinely unsettle you, in a good way. This isn't a roadmap for the 2060s. Toyota's solid-state timeline points at the late 2020s. Silicon anode EV batteries are already rolling into production vehicles today. Wireless charging pads are already sitting on nightstands around the world. The pieces aren't hypothetical. They're shipping, or they're a handful of years from shipping, at the same time, from the same country. And this is exactly the pattern that played out with the microwave. Nobody announces the battery is dead in a single dramatic press conference. It dies the way film cameras died, the way the CD died, the way the landline died. Quietly, piece by piece, one use case falling away at a time, until one day you realize you haven't thought about battery anxiety in months, and you can't quite remember when that stopped being a thing you worried about. So why does this keep happening in Japan specifically? Why is it always Japanese labs pulling on the thread nobody else wants to touch for 20 years? Part of it is resource scarcity. Japan has almost no domestic oil, gas, or significant mineral wealth. It imports the overwhelming majority of its energy. That national vulnerability has pushed decades of Japanese industrial policy and research funding toward energy efficiency and energy independence in a way that resource-rich countries never had the same incentive to prioritize. Part of it is simply cultural. The same obsessive, decades-long patience that produced 2,000 sketches for a single toaster and 1,000 hours of test toasting shows up again here, applied to something as unglamorous as a battery separator or an antenna resonance frequency. Nobody asked how to make lithium-ion slightly cheaper. Somebody asked why it catches fire at all, and then spent 20 years refusing to accept the answer, that's just how it is. If this is the kind of story that changes how you look at the everyday objects around you, the battery in your pocket, the box on your kitchen counter, that's exactly the kind of thing this channel exists to dig into. Hit subscribe now so you don't miss the next one, because it's coming soon, and it's about a piece of technology you use every single day without ever asking who actually built it, or why. So here's the payoff to the question from the very beginning. Why did it take 40 years to fix the battery? Because, just like the microwave, it was never actually finished. It was a brilliant compromise built under 1980s constraints, and everything since, the safety warnings on airplanes, the slow chargers, the phone that dies by 4 p.m., the cobalt mines nobody wants to think about, was scaffolding built around a flaw the entire industry quietly agreed not to talk about. Fixing it for real required people patient enough to spend decades on solid electrolytes and resonant magnetic fields and microwave beams from orbit. That patience turned out to belong to Japan, again, from 4 different directions at once. The battery on your desk right now, the one slowly dying as you read this, had one incredible trick. It was portable. That's it. That's the whole magic act. And for 40 years, that single trick was enough to make everyone forgive absolutely everything else. It made you forgive the fires, the recalls, the airplane bans, the warehouse blazes nobody talks about. It made you forgive the slow charging, the 30 minutes you've spent standing next to an outlet, watching a percentage crawl upward like it's doing you a favor. It made you forgive the mining conditions buried at the bottom of the supply chain, the ones most people never think about because the phone in their hand doesn't come with a label. It made you forgive the anxiety, that specific, modern anxiety of glancing at a battery icon and feeling your whole day quietly rearrange itself around a number. Portable was enough. Portable bought 40 years of silence. That forgiveness is running out. Because for the first time since Akira Yoshino built his first prototype in a lab decades ago, portable and permanent are no longer opposites. You no longer have to choose one or the other. And this isn't a rumor. It's not a concept render sitting in a press release, designed to generate headlines and then quietly vanish. It has a company name attached to it. It has a target production year, real engineers, real budgets, real deadlines. And in a lab in Kyoto, right now, while you're reading this, electricity is already floating through open air. No wire, no plug, no cable snaking across your desk, just a field and a receiver, and power moving between them like it was never supposed to need a wire in the first place. Meanwhile, you're sitting there, phone in hand, watching the battery icon count down like it's the only option that's ever existed. My guess is within the next decade, your kids are going to look at a charging cable the exact same way you look at a rotary phone cord today, a strange little museum piece. And they're going to ask you the one question that sums up this entire story. Wait, you had to plug it in? Why? And you'll get to tell them about a melted patent, a $2 payout that never quite happened the way legend says, a Nobel Prize awarded 30 years too late, and a country that finally decided good enough was never actually good enough. If this changed how you think about the thing charging in your pocket right now, the next video breaks down another everyday piece of technology, quietly being replaced as we speak. And this one starts with a mistake even stranger than a melted chocolate bar.